somewhere out there right now, the fabric of space itself is tearing apart, not slowly, not gently, but at an accelerating rate that our best equations cannot fully explain. For 30 years, cosmologists built what they believed was the definitive blueprint of the universe. A model so elegant, so mathematically satisfying, that it won Nobel Prizes and filled textbooks. It told us exactly what dark energy is, exactly how it behaves, and exactly how the universe will end, cold, empty, expanding forever into darkness. Then, in 2025, the Dark Energy Spectroscopic Instrument returned data that nobody expected. Data suggesting that dark energy, the invisible force driving everything apart, is not constant. It is changing. And if that is true, then everything we thought we knew about the fate of the universe, about the nature of space and time itself, needs to be rewritten from the first line. We are not talking about a minor correction to an equation. We are talking about the possible collapse of the foundational framework that modern physics stands on. And here is what makes this genuinely unsettling. Scientists do not yet agree on what is replacing it. The leading candidates contradict each other. Some suggest the universe will tear itself and everything in it completely apart. Others suggest it may one day stop, reverse, and collapse back into a single point. The universe is sending us conflicting signals, and we are only now beginning to have instruments powerful enough to listen carefully. Subscribe if you want to follow the questions that matter most. Now, let us begin. To understand why this discovery is so destabilizing, we need to go back to the beginning. Not the beginning of this story, the beginning of everything. For most of human history, we assumed the universe was static, eternal, unchanging. Even Einstein, when he first wrote down his equations of general relativity in 1915, found that they predicted a universe in motion, either expanding or contracting. He did not like that. So he added a term to his equations specifically to force the universe to stand still. He called it the cosmological constant. He later called it the greatest mistake of his life. Then in 1929, Edwin Hubble looked through a telescope in California and discovered that every galaxy he could see was moving away from us. And not just away from us, away from each other. The entire universe was expanding in every direction simultaneously. Think of it this way. Imagine the universe as a loaf of raisin bread rising in an oven. Every raisin represents a galaxy. As the bread expands, every single raisin moves away from every other raisin, not because the raisins themselves are moving through the bread, but because the bread itself is growing. That is exactly what space is doing. It is not that galaxies are flying through space. Space itself is stretching. This expansion is measured by what cosmologists call the Hubble constant, a number that describes how fast the universe is expanding at any given moment. The higher the number, the faster everything is flying apart. For decades, scientists assumed this expansion was slowing down. Gravity, after all, pulls things together. The mass of all the galaxies in the universe should be acting as a brake on the expansion, gradually decelerating it over time. Then in 1998, two independent teams of astronomers pointed their telescopes at distant exploding stars and measured something that stopped them cold. The expansion was not slowing down. It was speeding up. Something was pushing the universe apart faster and faster, working directly against gravity. They called it dark energy, and they had absolutely no idea what it was. That name, dark energy, it is not a description. It is an admission of ignorance dressed in confident language, a placeholder for something we detected but cannot explain. And it makes up 68% of everything that exists. Here is where the story stops being merely fascinating and starts being genuinely alarming. If dark energy exists and drives the expansion of the universe, then physicists should be able to measure that expansion precisely. And they have. The problem is that when two completely independent groups of scientists measure the same number using two completely different methods, they get two different answers. And the gap between those answers refuses to go away. The first method looks backward in time as far as physically possible. In the early universe, roughly 380,000 years after the Big Bang, the cosmos cooled enough for atoms to form for the first time. At that moment, light was released, a faint afterglow that still fills the entire sky today. We call it the cosmic microwave background. The Planck satellite spent years mapping this ancient light with extraordinary precision, and from that map, scientists extrapolated forward using the standard cosmological model to calculate how fast the universe should be expanding today. Their answer, approximately 67.4 kilometers per second per megaparsec. Think of this method like reading a diary written by the universe when it was an infant and using that diary to predict how fast it would be running as an adult. The second method works in the opposite direction. Rather than looking back to the beginning, it measures the universe as it exists right now using a cosmic distance ladder built from overlapping measurement techniques. At the top of that ladder sit Type Ia supernovae, exploding white dwarf stars that always detonate with nearly identical brightness. Because we know how bright they truly are, we can measure how faint they appear and calculate exactly how far away they are. Using this method, the measured expansion rate comes out to approximately 73.4 kilometers per second per megaparsec. Think of this as pointing a radar gun directly at the universe and measuring its speed in real time. 8%. That is the gap. 8% sounds modest. In cosmology, it is enormous. And critically, as measurements have become more precise over the past decade, the gap has not closed. It has held firm. The probability that this discrepancy is simply random measurement noise is less than 1 in 100,000. Then in 2025, the Dark Energy Spectroscopic Instrument added a third voice to this conversation. Using a method called baryon acoustic oscillations, essentially using the frozen imprint of ancient sound waves in the distribution of galaxies as a cosmic ruler, DESI found something that neither previous method had clearly shown. Dark energy does not appear to be constant. Its strength seems to have been different in the past than it is today. When the James Webb Space Telescope independently re-examined the distance ladder measurements in 2023 and confirmed the higher expansion rate, the last comfortable explanation evaporated. This was not a calibration error in aging instruments. This was not a statistical fluke waiting to be averaged away. 3 independent methods, 3 different physical phenomena, all pointing toward the same uncomfortable conclusion: something in our model of the universe is fundamentally wrong. The cosmological framework that has guided physics for 3 decades may be built on an assumption that the universe itself is now contradicting. The question is no longer whether something unexpected is happening. The question is what that something actually is. So if the standard model is breaking down, what replaces it? This is where the conversation shifts from established science into the frontier, the boundary where data ends and careful, mathematically grounded speculation begins. What follows are the leading candidates that physicists are currently taking seriously. None of them are confirmed. All of them are extraordinary. The first candidate is called quintessence. Unlike the cosmological constant, which treats dark energy as a fixed property of empty space, the same everywhere, always, quintessence proposes that dark energy is actually a dynamic field, a field that stretches across the entire universe and evolves over time, much like other fundamental fields in physics. Think of the difference this way. The cosmological constant imagines dark energy as a still lake, the same depth everywhere, unchanging. Quintessence imagines it as a river. It flows, it has a current, and that current has been slowing down. If quintessence is correct, it would elegantly explain what DESI observed in 2025, dark energy that was stronger in the past and is gradually weakening. The universe would continue expanding, but the acceleration would slowly ease over cosmic timescales. This is the gentlest of the candidates, but it is still entirely unconfirmed, and the field itself has never been directly detected. The second candidate is considerably less gentle. It is called phantom energy, and it represents a scenario where dark energy is not weakening but strengthening, growing more intense as the universe expands. In this model, the equation of state parameter, which physicists use to describe the behavior of dark energy, crosses below a critical threshold in a way that standard physics considers forbidden. The consequence of phantom energy, if it is real, is something called the big rip. As dark energy grows stronger, it would eventually overpower not just gravity between galaxies, but every other force in nature. Gravity holding galaxy clusters together, tears first, then the gravity binding individual galaxies, then the gravity holding solar systems together, then the electromagnetic force binding molecules, then atoms themselves. And finally, in the last fraction of a second before the end, the strong nuclear force holding atomic nuclei together would lose. Every proton, every neutron ripped apart into their constituent quarks. Some models place this event approximately 22 billion years from now. Others suggest sooner. This is a speculative scenario, not a confirmed prediction, but it emerges naturally from certain interpretations of dark energy data, and physicists take it seriously enough to model it rigorously. The third candidate is perhaps the most philosophically disorienting because it does not fit neatly into either of the previous categories. It emerges directly from the DESI 2025 data, and points toward a possibility that contradicts both quintessence and phantom energy simultaneously. What if dark energy is not simply weakening gradually, as quintessence suggests, but oscillating, behaving more like a wave than a river, with periods of strengthening and weakening that cycle over cosmic time? This would produce exactly the kind of tension between different measurement epochs that we are currently observing. If this oscillating model holds, the future of the universe becomes genuinely unpredictable. Under certain parameters, the expansion could eventually reverse entirely, leading to what cosmologists call the big crunch, all of space collapsing back into a single infinitely dense point. Under other parameters, a new expansion could follow, a new universe born from the collapse of this one. Here's the critical thing to hold on to as you consider these candidates. The data from DESI, from James Webb, from Planck, all of it is real. The tension between measurements is real. What remains unresolved is the interpretation. Each of these candidates is a serious scientific hypothesis under active investigation. None of them is the answer yet. The universe has handed us a set of clues that do not obviously fit together. And scientists around the world are doing what scientists do, building models, testing predictions, and waiting for the next generation of instruments to deliver the evidence that will finally tell us which story the universe is actually telling. To truly understand why dark energy is so difficult to explain, we need to go one level deeper, because the crisis we are describing is not just a disagreement between two measurements. It is a symptom of a far older and far more fundamental fracture running through the entire foundation of modern physics. We have two theories. Both are extraordinarily successful. Both are supported by overwhelming experimental evidence, and they are fundamentally incompatible with each other. The first is Einstein's general relativity. It describes gravity as the curvature of space-time, a smooth, continuous fabric that bends in the presence of mass and energy. It works with breathtaking precision at large scales. The orbits of planets, the bending of light around galaxies, the expansion of the universe itself, general relativity handles all of it with extraordinary accuracy. The second is quantum mechanics. It describes the behavior of matter and energy at the smallest possible scales, the world of electrons, photons, and quarks. At that scale, nothing is smooth or continuous. Everything is discrete, probabilistic, and fundamentally uncertain. Quantum mechanics is arguably the most precisely tested theory in the history of science. At their respective scales, both theories work flawlessly. The problem is that the universe does not respect the boundary we have drawn between them. And nowhere is this collision more catastrophic than in the concept of vacuum energy. Quantum mechanics predicts that empty space is not actually empty. At the smaller scales, pairs of particles and antiparticles are constantly flickering in and out of existence, borrowing energy from the vacuum, annihilating each other and disappearing again. This process generates what physicists call vacuum energy, and it should contribute to the cosmological constant. It should, in other words, look exactly like dark energy. Here's the problem. When physicists calculate how large this vacuum energy should be based on quantum mechanics, and then compare that prediction to what we actually observe, the discrepancy is staggering. The theoretical prediction is larger than the observed value by a factor of 10 to the power of 120. That is not a rounding error. That is the largest discrepancy between a theoretical prediction and an experimental observation in the entire history of science. Think of it this way. Quantum mechanics predicts the height of a person to be roughly 10 billion kilometers. We measure 1.7 meters, and we do not know why. This is called the cosmological constant problem, and it sits at the heart of everything we have discussed in this video. It tells us that either quantum mechanics is missing something fundamental at high energies, or general relativity breaks down in ways we have not yet detected, or both theories are approximations of a deeper framework that nobody has yet discovered. The universe is not hiding dark energy from us out of cruelty. It is simply operating according to rules that our current language of physics is not yet equipped to fully describe. And that is perhaps the most honest thing science can say right now. Stop for a moment and look at your hand. What you are seeing is not solid matter in any meaningful sense. The atoms that make up your skin, your bones, your blood, they are almost entirely empty space. If you took a single hydrogen atom and expanded it to the size of a cathedral, the nucleus would be a grain of sand sitting in the center, and the electron would be a speck of dust somewhere near the outer walls. Everything in between is vacuum, and that vacuum is not empty. It is the same vacuum we have been discussing, the same space that is stretching, The same space threaded with dark energy, flickering with quantum fluctuations, participating in the expansion of the universe at every scale simultaneously. The force that is pulling galaxy clusters apart from each other right now is present in the space between your atoms. You're not separate from what is happening out there across billions of light years. You are made of the same fabric. You are a temporary configuration of matter held together by electromagnetic forces and the strong nuclear force floating inside a medium that the universe is actively expanding. Right now, as you watch this, dark energy is present in every cubic centimeter of space inside your body. The only reason you are not being torn apart, along with the galaxy clusters, is that gravity and electromagnetism are locally far stronger than the current intensity of dark energy. Currently, that word carries weight when you understand what the candidates in the previous section are actually proposing. You are not an observer of this story. You are inside it, woven into the fabric that is tearing. Before we go further, intellectual honesty requires something important. Everything presented so far deserves a serious counter-argument, and that counter-argument exists, and it comes from careful, rigorous scientists who are not dismissing the anomalies. They are simply proposing a less dramatic explanation for them. The most prominent skeptical position holds that the Hubble tension is not evidence of new physics. It is evidence of accumulated systematic error in the cosmic distance ladder. Every rung of that ladder, from Cepheid variable stars to type Ia supernovae, requires calibration. And each calibration step introduces its own assumptions, its own potential sources of bias. Stack enough of those together, and a discrepancy of 8%, while surprising, is not necessarily impossible to explain through conventional means. This is not an unreasonable position. Science has been here before. In the early 20th century, anomalies in the orbit of Mercury were attributed by some astronomers to an undiscovered planet sitting between Mercury and the Sun. They even named it Vulcan. It did not exist. The anomaly was real. The exotic explanation was wrong. The correct answer turned out to be general relativity, but the lesson holds. Anomalous data does not automatically demand the most dramatic available interpretation. However, there is a meaningful difference between the Hubble tension and historical measurement disputes. When the James Webb Space Telescope re-examined the Cepheid variable calibrations that underpin the distance ladder in 2023, it did not find the systematic errors that skeptics had hoped for. The higher expansion rate held when DESI used baryon acoustic oscillations, a method with entirely different systematic vulnerabilities. It independently found signals consistent with evolving dark energy. When three methodologically independent approaches converge on similar anomalies through completely different potential failure modes, the probability that all three are wrong in the same direction decreases substantially. As physicist Adam Rees, one of the Nobel laureates who originally discovered cosmic acceleration, has noted, the tension has only grown more statistically significant as instruments have improved, which is the opposite of what you would expect from a systematic error being gradually identified and corrected. The universe does not care how elegant our models are. It does not adjust its behavior to spare us the inconvenience of rewriting our textbooks. The data is what it is. And right now, the data is not cooperating with the comfortable explanation. The good news, if you can call it that, is that we will not have to wait forever for answers. Beginning in 2026, the Vera Rubin Observatory in Chile will begin its legacy survey of space and time. Every few nights for a full decade, it will image the entire southern sky. The expected yield is staggering. Thousands of gravitationally lensed quasars and hundreds of lensed supernovae. This single dataset is projected to reduce the uncertainty in the Hubble constant to below 1%. If the tension survives that precision, it becomes effectively incontrovertible. Running in parallel, the European Space Agency's Euclid satellite is already operational and building a three-dimensional map of the large-scale structure of the universe stretching back 10 billion years. Its primary mission is to trace how dark energy has evolved across cosmic time, exactly the question that DESI raised in 2025. Further out in the 1930s, the Laser Interferometer Space Antenna, LISA, will detect gravitational waves from space itself, providing a measurement of the Hubble constant that requires no light, no stars, and no distance ladder whatsoever. A completely independent measurement using an entirely different physical phenomenon. By 2035, we will almost certainly know whether the Hubble tension represents measurement error or genuinely new physics. The instruments are being built, the observations are accumulating. The answer is approaching, and whether we are ready for it or not, we began this conversation with a universe tearing itself apart. We end it with something more unsettling than any of the specific scenarios we discussed. We end it with uncertainty, not the comfortable uncertainty of a problem almost solved, but the deep uncertainty of a field standing at the edge of its own framework, looking down into something it does not yet have the language to describe. Every candidate we examined, quintessence, phantom energy, oscillating dark energy, remains unconfirmed. The tension is real. The cause is not yet known. Perhaps the most important thing science has ever produced is not an answer. It is the discipline to sit with an open question and resist the temptation to close it prematurely. The universe is 13.8 billion years old. We have been listening carefully for roughly 100 years. We are just getting started.